Hello, my name is Marvin Tammen, and it's my pleasure to welcome you to my fully virtual presentation of the ICASSP 2020 paper, DNN-based speech presence probability estimation for multi-frame single microphone speech enhancement. This paper is authored by Marvin Tammen, who is myself, Fischer, Meyer, and Simon Doclo, all from the Department of Medical Physics and Acoustics in Oldenburg, where I'm currently a PhD student. So please enjoy.
So let's get to the slides. First, a brief outline of my presentation. I will start by stating the problem we are trying to deal with and follow with the framework we are using to do so, the multi-frame filtering framework. After explaining how we estimate the parameters we require, I will present simulation results and finally conclude the talk with a brief summary and a bit of outlook. So let's get to the problem statement. We find ourselves in a situation where a single microphone is available. However, in addition to a speech component X that we want to record, we also record noise N, which may or may not be non-stationary, but which in any case is non-speech. To deal with this situation, many approaches first transform the signal to a different domain, for example, using a short-time Fourier transform, where the signal is then filtered and transformed back, giving an estimate of the speech component. For example, recently the use of masking-based approaches has exploded, which apply real-valued mask to the microphone SDFT coefficients. Also, the Wiener gain can be associated here. The drawback of such an approach is that noise reduction goes hand in hand with speech distortion. For this reason, multi-frame approaches have been proposed, which apply a complex-valued FIR filter to more than one frame to get one enhanced frame. Theoretically, they can reduce noise without distorting the speech, which usually comes at the cost of a more difficult estimation process. So the main contribution of this work is the inclusion of a deep learning approach in this difficult estimation process, which is not dissimilar from the masking-based approaches I just mentioned. So now let's talk about multi-frame filtering, about the model and assumptions we are making, and how these are used. First, we consider additive noise. Here, the vector y at frequency index k and time index l contains the n most recent noisy STFT coefficients, as you can see here. K will be omitted in the following since all frequency bins are treated independently. Second, we assume that speech and noise are independent, so that we can write the noisy correlation matrix as the sum of the speech and noise correlation matrices. Third, we assume that we can separate the speech component into a correlated and an uncorrelated component. The normalized speech interframe correlation vector gamma x, and that's a long word, describes the correlation between the current frame and all time frames that are referenced in this vector, and it's defined via the speech correlation matrix phi x. So how can the speech correlations help us in designing a noise reduction filter? Wang and Benesti have proposed optimization goals, which actually might seem quite familiar. First, the output power is minimized, and second, they add the constraint of preserving the speech correlation over time. So this results in the multi-frame variant of the well-known minimum power distortionless response filter. For that, we need to estimate the noisy correlation matrix and the normalized speech IFC vector. So let's proceed with how we estimate these parameters. First, we deal with the speech IFC vector, gamma x. Using the a priori SNR, xi, which is defined at the right side as the ratio of speech and noise power, we can write the speech IFC vector as a linear combination of the noisy and the noise IFC vector, which are defined similarly as the speech IFC vector. This may intuitively be easier to estimate, since the noisy signals are available anyway, and the noise IFC vector might be less time varying than the speech IFC vector. In fact, Chasser and Martin have proposed a maximum likelihood estimator, where the noise IFC vector is just a constant that depends on the used STFT frame overlap. We denote this one with mu. As an alternative, we replace this constant noise IFC vector with an adaptively estimated one, which is denoted by gamma. So the difference between these estimators is whether we use a constant deterministic noise IFC vector estimate or an adaptively estimated one. Also, as you can see, we now require an estimate of the a priori SNR, for which we use the decision-directed approach. Note that the DDA requires a noise PSD estimate, which we can extract from the noise correlation matrix. Okay, so next up, correlation matrices. For the noisy correlation matrix, we apply recursive smoothing to the microphone signals with a fixed smoothing constant lambda y. For the noise correlation matrix, the process looks pretty similar, only that we now have an adaptive smoothing parameter lambda n that depends on the speech presence probability, SPP. This SPP-based recursive smoothing approach has been proposed by Cohen. In the first extreme case, that the SPP estimator tells us there is no speech, so we expect noise, and thus update the noise correlation matrix relatively quickly. In the second extreme case of only speech, we do not update the noise correlation matrix. And of course, there are situations in between. So as you might have guessed, if you're still awake, the next and also final parameter that we need to estimate is the SPP. Here, as the reference approach, we use the maximum likelihood-based approach proposed by Gergman and Hendricks. And in the proposed alternative, deep learning comes into play. We let a deep recurrent neural network estimate it for us. The architecture is actually inspired by the neural beamformer architecture, that is a bidirectional long short-term memory layer, followed by some linear layers with ReLU activations. As the input feature to this DNN, we use the STFT magnitudes of the whole utterance. Since the target is a probability, a sigmoid output activation is used here to ensure values between 0 and 1. And the RNN is trained to minimize the mean square error between the estimated SPP and the target SPP, for which we use the one from Gergman and Hendricks. So, since this was a rather large number of different parameters, let's go through the method again. After transforming our signal to the STFT domain in this block, we use either an ML-based or a DNN-based SPP estimator here. Using this SPP estimate and the noisy STFT coefficients, we use recursive smoothing here in order to estimate the correlation matrices. When computing the speech IFC vector, we use either the maximum likelihood constant noise IFC vector or the adaptively estimated noise IFC vector. And then, since we are interested in seeing the effect of multi versus single frame filtering, in the filtering stage, we construct either the multi-frame MPDR filter or the single frame Wiener gain, which is of course not depending on the speech IFC vector. Now that you've probably heard the word estimate a sufficient number of times, let's go over to the experiments. For training and testing, we use the following datasets. For speech material, Wall Street Journal sentences, and making sure that there's no overlap between training and testing. For noise, we use the NoiseX92 database for training, and for testing, the Aurora database. And regarding SNRs, for training, we uniformly sample between 0 and 20 dB, while for testing, we consider -5 to 20 dB in steps of 5 dB. So all the while making sure that the training and testing datasets are disjoint. And also it's important to mention that we have one DNN that is trained for all SNRs. So regarding some of the settings that are used in the algorithms, we use rather short STFT frames to increase the speech correlations so that we can actually exploit them. For the recursive smoothing constants, we have chosen them empirically. The filter size n is set to 18, which means that 21 milliseconds of speech correlations can be utilized. Also, we apply a minimum gain of -17 dB to all considered filters in order to reduce musical noise. So during the training of the DNN, we apply common procedures, which includes batch normalization, dropout, and early stopping. And for the optimization of the parameters, we use the ADAM optimizer. Evaluation is done in terms of PESC improvement, so improvement over the noisy signal, where the clean signal is given as the reference. So let's get to the results. In this figure, you can see the PESC improvement versus the input SNR averaged over the different noise types and speakers. At the top, the average noisy values are displayed. So first in blue, we have the ML, so maximum likelihood, constant noise IFC vector, using either the ML or the DNN-based SP estimator. Green depicts the adaptively estimated noise IFC vector, again using the ML or DNN-based SVP estimator. Finally, in red, we have the Wiener gain methods, again using the ML or DNN-based SVP estimator. So first, we can see that dark blue, the MPDR using the DNN-based SVP and the ML constant noise IFC vector performs the best except for 20 dB input SNR, which remains a special situation. Second, we compare light versus dark colors. So for example, this is light, this is dark, this is light, this is dark, which codes for DNN-based versus ML-based SVP estimator. Here, a clear trend towards the DNN estimator, the darker colors can be seen. Third, we compare blue and green, so here and here, which codes for using the ML constant noise IFC based estimator versus the adaptively estimated noise IFC based estimator. And here a clear trend towards the ML constant noise IFC based estimator can be seen, so to blue. Finally, we can make out that the multi-frame approach is blue and green. These four tend to a higher performance than the Wiener gain in red. So, concluding this talk, we consider the multi-frame single microphone speech enhancement approach. We improved objective speech enhancement performance by replacing a conventional ML-based SVP estimator with a DNN-based SVP estimator. And we confirmed that multi-frame filtering can be advantageous to single-frame filtering using a Wiener gain. Regarding future work, we want to improve the performance by tightly integrating this filtering process into the training process of the DNN. Here we could also consider giving the DNN more power over the estimation process. So, I thank you for your attention. If you have any questions, then just please shoot me an email.
Please stay safe, and perhaps we'll see each other next year at ICASSP 2021. So goodbye.